Hey everyone! Welcome back to my channel Zab Explains. Now if you are new to this channel, I am your host Zubair. Today we're diving deep into the world of networking by exploring two of the most crucial protocols that drive the internet, TCP and UDP. In this video we'll break down what TCP and UDP are, the differences between them, how their headers are structured, and why it all matters in the world of networking. So, whether you're studying for your networking certification, or just curious about how data moves across the internet, this video is for you. Introduction to TCP and UDP. Before we jump into the headers, let's quickly go over the basics of TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP is a connection-oriented protocol, meaning it establishes a connection between the sender and receiver before any data transfer occurs. It's designed to ensure reliable, ordered, and error-checked delivery of data. Think of TCP as sending a package with a receipt to make sure it's received in the right order. UDP, on the other hand, is connectionless. It doesn't establish a connection before sending data, and there's no guarantee the data will arrive in order, or be free from errors. It's much faster, but there's no safety net. This is why UDP is commonly used in time-sensitive applications like online gaming or video streaming. Now that we know what these protocols do, let's break down their headers to see how each one achieves its goals. The TCP header breakdown. Let's start by looking at the TCP header. It's more complex than UDP because TCP needs to ensure reliable communication. The TCP header contains several fields that are vital for managing data transmission. Let's go through them one by one. 1. Source port and destination port, 16 bits each. These fields identify the application or process on the sender and receiver sides. The source port tells us where the data came from, while the destination port indicates where it's going. 2. Sequence number, 32 bits. This is crucial for ensuring that data packets arrive in the correct order. The sequence number marks the position of this segment's data in the overall sequence of the data stream. 3. Acknowledgement number, 32 bits. This is used in the acknowledgement process to confirm receipt of data. If the ACK flag is set, this number will indicate the next byte expected by the receiver. 4. Data offset, 4 bits. Also called the header length, this tells us where the TCP header ends and the data begins. It's important because it allows variable length options in the header. 5. Reserved, 3 bits. These bits are reserved for future use and are usually set to 0. 6. Control flags, 9 bits. These flags control the state of the connection. Some key flags include SYN, used to initiate a connection. ACK acknowledges the receipt of data. Und fin indicates that the sender has finished sending data. RST resets the connection. PSH pushes data to the receiving application immediately. Urgent indicates urgent data. 7. Window size, 16 bits. This field is part of the flow control mechanism. It specifies the amount of data, in bytes, that the sender is willing to receive without acknowledgement. 8. Checksum, 16 bits. The checksum helps ensure data integrity by checking for errors in the header and data. 9. Urgent pointer, 16 bits. If the URG flag is set, this pointer tells us where the urgent data ends within the segment. 10. Options, variable length. The options field is not always present but allows for features like window scaling and time stamping. If options are used, the data offset field will reflect their length. 11. Padding, variable length. The padding field is used to ensure the TCP header is a multiple of 32 bits. This is necessary because of the data offset's length requirements. That's a lot of information packed into a single TCP header. It's structured to ensure that data is delivered reliably, in the correct order, and error-free. The UDP header breakdown. Now let's look at the UDP header, which is much simpler than TCP. Since UDP is designed for speed and not reliability, its header is only 8 bytes long. Here are the fields. 1. Source port and destination port, 16 bits each. Just like in TCP, these fields identify the source and destination processes or applications. 2. Length, 16 bits. This field indicates the total length of the UDP packet, including the header and the data. 3. Checksum, 16 bits. The checksum in UDP is optional and is used for error checking. It covers the header, data, and a pseudo-header. While it can detect errors, UDP does not attempt to fix them or request retransmissions, making it less reliable than TCP. Unlike TCP, UDP doesn't have fields for things like sequence numbers, acknowledgements, or flags, which makes it more lightweight and faster for certain applications. Comparison of TCP and UDP headers. Let's compare the two headers side by side to understand why TCP is considered more reliable and UDP is faster. TCP has a more complex header because it needs to ensure reliable delivery of data. Features like sequence numbers, acknowledgements, and flow control are designed to provide error-free and ordered communication. UDP, on the other hand, is much simpler, which reduces overhead and increases speed. There's no error correction, flow control, or sequence tracking, making it ideal for applications where speed is more important than reliability. When should you use each? TCP is perfect for situations where accuracy is key, like sending emails, browsing the web, or transferring files. UDP is often used in time-sensitive applications, such as streaming media, gaming, or DNS lookups, where the occasional packet loss isn't a big deal. Real-world examples. Let's take a look at some real-world examples to better understand when TCP and UDP are used. TCP applications. Think about web browsing, HTTP, HTTPS, file transfers, FTP, and sending emails, SMTP, IMAP, POP3. In all these cases, reliable data transfer is crucial. UDP applications. UDP is used in online gaming, video conferencing, and live streaming. In these scenarios, the priority is speed and low latency, even if some data packets are lost along the way. Conclusion: to wrap things up, we've covered the differences between TCP and UDP, the structure of their headers, and how they're used in the real world. TCP ensures reliable, ordered data delivery with error checking, while UDP prioritizes speed and efficiency. Understanding the headers of these protocols helps you see how they achieve their respective goals and why they're used in different types of applications. If you found this video helpful, make sure to like, subscribe, and hit the bell icon for more in-depth networking tutorials. Leave a comment if you have any questions or want to see a specific topic in the next video. Thanks for watching, and I'll see you in the next one.